So welcome everybody. I'm happy to see so many young faces. Those of you who don't know me, my name is Peter Gradwohl. I'm a hydrogeologist actually, but I'm here to represent the President's Office of the University. I'm the Vice President for Research and Innovation. Welcome to the Matariki lecture today. I guess nobody knows what that is. Matariki is a university network established in 2011 of 7 nationally leading and comprehensive universities, as the University of Tübingen, some of the most historic universities in their countries. Besides Tübingen, we have members from the United States, the Dartmouth College, Durham University, our guest today comes from there in the UK, University of Otago in New Zealand, University of Western Australia, Queen's in Canada, and Uppsala University in Sweden. Matariki lectures are meant to showcase a researcher from another member institution and highlight individual collaborations. So this is what we will do today, and this is the second Matariki lecture in this series. And I can already announce the next one will be in New Zealand, University of Otago. So if you plan to go to New Zealand in 2019, you could attend the 150th anniversary of the Otago University and maybe see a Matariki lecture there. Maybe Todd Ehlers goes there or somebody else. So our guest of today, Alex Densmore, is professor at Durham's University Department of Geography, and he is a member of the Institute of Hazard, Risk and Resilience. And he has been working with my colleague, Todd Ehlers, during the summer, I guess, but already since several years. A warm welcome to you, and Todd Ehlers will later introduce you. So that's most what I have to say. I have to make a few announcements. The lecture will be recorded and will be put onto the webpage, so if you are interested or your colleagues are interested, they can also see it later on. And last but not least, maybe the most important is, after the lecture we will have a reception in the Kleine Senat. So free food and drinks and so on. So thank you very much for that, and I hand over to Todd Ehlers.
Thank you, Peter, and thank you to everyone for coming here. So I'm very pleased to introduce Alex Densmore. As Professor Gradwohl mentioned, he comes from Durham University, and although he's currently based between the Institute of Hazard, Risk and Resilience and the Department of Geography, he also has a strong background in geosciences and geology. Just to give you a little bit of background on Alex, as you'll see once he starts talking, he's an American. He completed his PhD from the University of Santa Cruz in 1997. And for those of you that have not been to Santa Cruz, this is actually probably the nicest place in the world to do a PhD. Very nice location. Following that, Alex then went to Trinity College in Dublin to the Department of Geology, and he was a lecturer there for several years. And then following that, he went with a colleague to the ETH in Zurich, and he was there for 5 years as an Ober assistant in the Geosciences department. Since 2006, Alex has been at Durham University, initially as a reader, and then worked his way up. He's now been promoted just this year to the second-level professor there. So congratulations on that. As you'll see from Alex's talk today, his research interests are quite diverse, but what he's well known for is being a global authority on landsliding and active tectonic processes, as well as erosion and sediment transport in mountain ranges. And what's particularly interesting about his work is that over the last couple of years in particular, he's worked quite heavily towards linking the scientific studies and aspects of this to hazards topics as well. He's won several awards throughout his career. The most notable one would be the Bigsby Medal from the Geological Society of London, and he's widely recognized in international circles within Europe and the US for his research as well. Just a few kind of noteworthy aspects that I'll mention related to his career. The first is, and one thing I really respect from his work, is his sense of community and societal outreach. And he's been involved in a number of non-academic organizations, for example, the UK Department of International Development. He's helped advise different UN organizations and a number of NGOs in Nepal. He's also provided advice to the government on India on groundwater-related issues. And so a lot of this has gone on in the aftermath of several big earthquakes that have occurred. One of them we'll hear about here today, but also he's done quite a bit of work related to the Wenchung earthquake in China in 2008. In terms of professional accomplishments, Alex is well known in our community for being someone who produces really high impact work that's detail oriented and pretty much leaves no stone unturned. And it's refreshing to have colleagues like that in an era where there's a lot more emphasis being placed on volume of material produced rather than quality. His efforts are also quite distinguished in the sense that he's the former editor-in-chief of the Journal of Geophysical Research, Earth's Surface. I'll just conclude briefly with a few personal notes on my interactions with Alex. So I actually first got to know Alex when I was a PhD student, and he's several years ahead of me in terms of his career, but I kept reading some nice papers by this guy, Alex Densmore. And then after a couple years, I heard that one of the areas I was interested in working in, he was also working there. And so I arranged to actually meet him in the field in the western US, where we were both interested in active tectonic processes. That meeting went quite well, and we've kept in touch over the years. And what I can say is that more recently, the way this developed was that I applied for a fellowship at Durham, and he hosted me there earlier this year. What we did while I was there, what we've been working on is a long-standing problem in the geosciences, and that focuses on trying to understand how climate change impacts rivers and river erosion rates globally. And you won't hear about that today, but that's ongoing work that we're doing. So I'd like to thank you, Alex, very much for taking the time out of your busy schedule to come here. And as part of the Matariki network of universities, we're very pleased to have you here and to host you. Just add a few other, so Peter Grothwald mentioned that we have a reception following this. And I should also mention Alex will be around my office tomorrow also, so if you're interested in talking with him, just talk to me briefly afterwards and we can set up a time. And we'll allow a few minutes for questions after his talk. So thank you, Alex, and the floor is yours.
Well, thank you very much, Todd, for that introduction, and thank you to Professor Grothwald as well. Thank you all for coming to hear this lecture on Wednesday evening. It's a pleasure in particular to be here on behalf of the Matariki network. The network has a real commitment to high-impact research that has a social dimension to it. And the network also has as one of its research themes, risk studies. And I think both of those are relevant to the work that I'm going to talk to you about this evening. This is really an overview of work that has been done by me with a number of colleagues over the last few years. And their names are listed up on the screen. In particular, Nick Rosser, Katie Oven, and Tom Robinson have been heavily involved in this, and I'll show you some of the work that they have led. And we've also been quite closely involved with an NGO, a non-governmental organization in Nepal called the National Society for Earthquake Technology, and they have been absolutely critical to this work, and so I want to acknowledge their contribution as well. So the background to this, or the motivation for why I'm interested in this topic, is really the challenge that earthquakes pose for us. So large earthquakes are the most expensive natural disasters that we face. And those losses are almost entirely uninsured, particularly when you look at emerging economies, emerging parts of the world. So an event like the 2011 Tohoku earthquake in Japan had cost in excess of $200 billion. Earthquakes also kill people, and something like 2 to 2.5 million people have died in earthquakes since 1900. Most of those, it turns out, did not die in the types of earthquakes like the Tohoku earthquake or the 2004 Sumatran earthquake, the very, very large magnitude earthquakes that happen in subduction zones around the world. Most of the deaths in earthquakes happen in smaller earthquakes, smaller events that happen in the continental interiors. And those are those red colors in the bar graphs that you can see. And there are a couple of reasons for that. In the continents, plate tectonics as a theory breaks down a little bit. The deformation or the relative plate motion is taken up on distributed networks of faults. So there are many different potential sources of seismic hazard. Because there are many faults, the return times of earthquakes on individual faults can be very long. They can be thousands or even tens of thousands of years. And so cultural memory of earthquakes and cultural adaptation to earthquakes are more limited. And the simple fact that people live much closer to the faults. They live closer to the sources of the seismic energy. And so when we have good information on earthquake hazard, I think it's important to say that we're capable of mitigating that to a pretty impressive extent. So I mentioned the Tohoku earthquake in Japan. It was a magnitude 9.0. It devastated large parts of the island of Honshu, and yet the death rate in terms of people who were exposed to the really high-intensity shaking was very, very low. And most of the fatalities in that earthquake were caused by the tsunami that followed. But contrast that with a much smaller earthquake that occurred in Iran in 2003, the Bam earthquake, a magnitude 6.6. And the death rate there was something like 30% of the people who were exposed to high-intensity shaking, something like 26,000 fatalities. And most of the really deadly earthquakes in the past 25 years have come as a surprise, either in places that we didn't expect, or on faults that we didn't think were particularly active, or on faults that we didn't think were capable of generating the size of the earthquake that we experienced. So, to deal with this challenge, there have been a number of calls over the last decade or so to make better use of science, to actually bring our scientific understanding of earthquakes and earthquake hazard to bear in reducing the risks from earthquakes. And there are various ways in which this has been expressed. There's a quote here from the UN ISDR about how important scientific enterprise is for supporting mitigation, but also for developing policy. And a really nice quotation that I think captures the essence of this. For that to work, science has to be useful, it has to be usable, and it also has to be used. If one of those three things doesn't happen, then our scientific knowledge, the science that we do and the information, the understanding that we gain is really not being put to best use. So that raises a question. What is it that we need? What kind of science? And how can we do this most effectively? And that's really one of the things that we've been trying to work on over the last few years. I've chosen to focus this particular talk on Nepal and the work that we've done in Nepal for a couple of different reasons. Nepal has been subject to a series of very large, very damaging earthquakes. Those in the historical record go back to 1505. In fact, there's good evidence of even earlier earthquakes, 1255 in particular, the most recent of which was in 2015. Nepal also suffers from persistent, widespread landsliding. Most of this is triggered in the annual South Asian monsoon, and I'll show you some examples of what that looks like in a moment. The hazards that earthquakes and landslides pose are therefore everybody's responsibility. They affect the entire country. And yet at the same time, historically, they have been nobody's responsibility. So Nepal only enacted a national disaster management framework, a piece of legislation to cover the governance of natural disasters in 2017, and the Natural Disaster Management Agency is only now being set up. Before that time, disasters had a tendency to fall through the cracks. So different ministries, different departments couldn't agree on who was responsible for earthquakes, for landslides, for flooding. Nepal also has a large national and international NGO presence. Non-governmental organizations have taken up a lot of the functions of government in Nepal for various reasons that I won't go into. Those organizations are active in various phases of Nepali life as humanitarian organizations, but also in terms of community development and disaster risk reduction. So if we can work with those organizations, we have a chance potentially for very broad impacts, because many of these are organizations that work across the globe. But we also have to cope with the fact, or deal with the fact, that many of those organizations have relatively limited capacity in themselves to generate science. That's not their primary function. Okay, so a little bit of geological background, since many of you have an earth sciences interest. I mentioned that Nepal has suffered from a number of historical earthquakes. This is an attempt to look at the patches or rupture areas in many of those earthquakes. You can see that for some of them, the magnitude is somewhat well constrained. For others, there are question marks. We don't know the exact dimensions of the rupture patch, and we don't know how much slip was released. But the largest earthquakes there, the 1505 earthquake, for example, in western Nepal, or the 1950 earthquake in Assam, east of Nepal, are capable of something like a magnitude 8.8, 8.6 to 8.8. These are very, very large events, and if they were to recur, would have extremely devastating consequences. Most of those earthquakes, but not all, occur along the Himalayan frontal fault or Himalayan frontal thrust system. This is a picture of one of the few places where the Himalayan frontal thrust is actually exposed at the surface. In other places, it's concealed, and we need to dig in order to find evidence for it. In terms of landsliding, landslides, as I said, are pervasive throughout the middle hills and the higher parts of Nepal. On average, over the last couple of decades, there have been something like 35 fatal landslides per year. Most of those landslides are relatively small. They kill a relatively small number of people, but in total, the average death toll is something like 200. Almost all of those occur during the monsoon, as I'll show you in a moment. Because of their size and because of their location, they're very difficult to predict, and they're almost impossible to engineer. So the idea that we could impose some sort of hard engineering solution in order to stabilize hill slopes across Nepal is really not particularly practical. There are many contributing factors: earthquakes, monsoon rainfall, but also road construction is a major factor in triggering landslides. And in fact, landslides have a persistent and recurrent impact on the road network, to the point where many rural roads are simply abandoned during part of the monsoon and then recut after the monsoon rains have finished. And so when you look at the pattern of landslide fatalities across a typical year in Nepal, and this is about a decade worth of observations that have been averaged, what we're looking at here is a histogram of the average number of fatal landslides per day, going from the beginning of the year on the left-hand side to the end of the year on the right-hand side. And you can see there's very little activity up until about the middle of June, which coincides with the onset of the South Asian monsoon. Landslide activity spikes immediately after the onset of the monsoon, and then it decays, and around about this time of year, sort of mid-October or so, it drops back effectively to zero, and it stays at that level until the following year. So remember that pattern, because this is something that we're going to come back to in the context of the 2015 earthquake. Okay. So given this history of damaging events, and given this, this broad national and international engagement in Nepal, it's not too surprising that there are a number of hazard maps. There have been a lot of attempts to assess various hazards at the national level and at the subnational level. So these are simply two examples of that. The upper image is an earthquake hazard map showing the expected level of shaking, peak ground acceleration with a 2% probability over the next 50 years. The lower image shows the likelihood of landsliding during a large earthquake. These are two separate studies. I chose them more or less at random. Similar hazard maps exist for flooding, for drought. But the question really is, how much of this science is actually being used to reduce the risks of disasters? So, as a physical scientist, this isn't a question that I would normally ask. But as part of a larger project looking at the role of science and scientific knowledge in earthquake risk reduction, we ask people. So we set up a series of focus groups with Nepali scientists, with practitioners who were engaged in community-level work, with donor organizations like the Department for International Development, and with government officials. And we really wanted to know what scientific knowledge was being used currently to inform earthquake risk reduction. What were the scientific needs that risk reduction community saw? In other words, what did they want to know? And what were the opportunities or the barriers associated with that? And the results, again, as a physical scientist, were surprising to me. Because the first finding was really that earthquake science is not really used in any kind of meaningful operational sense. It's used in very limited ways, primarily to get risk reduction onto the agenda of government. So to convince government that there is a problem that needs to be addressed and that requires resources. To some extent also to raise awareness of earthquakes in communities, but for these purposes, the kind of in-depth technical knowledge that we might generate, the understanding about exactly where a fault is, or exactly when the last earthquake was, and how much slip it had, and what its paleomagnitude was, that was really not seen by anyone as relevant for risk reduction. The second surprising finding to me was that the kind of probabilistic hazard maps that I've just shown you, which we might think of as the kind of primary outputs from earthquake science, really weren't used at all. They were seen as difficult for non-technical experts to interpret. They were seen, particularly at the national scale, as lacking the detail that you might need in order to inform any kind of meaningful planning or any community-based activities. And they were really seen mostly as useful only as an advocacy tool. In other words, you could point to these maps and say, look at all the red areas, clearly there's a problem here, and then move on. And that's kind of the end of the role of science in this process. In terms of what the humanitarian organizations actually wanted to know, the primary thing was, well, where is the next earthquake going to occur, and when? So can you predict the next earthquake? And as soon as you tell them no, then the conversation sort of dwindles a little bit. They wanted to know state-of-the-art facts, but they wanted to be able to use those for advocacy. In other words, to speak with some credibility, so that it wasn't seen as something that an organization just made up, but that there was actually some scientific basis for the claims. They particularly wanted to understand landslides and landslide hazard. This was seen as something which was not currently well understood. And they really wanted to know local scale information. The finer, the better, because that's what could actually be turned into operations. That's what could actually be used for planning activities on the ground. So I just want to pause there and think about what the lessons of this might be. So we have evidence of very limited use of science for earthquake risk reduction across Nepal, despite the fact that there's very real and very widely perceived hazard. There's a finding that hazard maps are really not relevant, and that puts the onus on us as scientists to think about, well, what useful outputs might we be able to generate if these things that we're doing are not being used and are sitting on shelves. Landslides were seen as a key unknown, and the other finding that came out of this really was that these relationships take time to build, and it takes time to build trust between the organizations that we were engaging with and the scientific community. It's not something that happens overnight. So, what do? How do we make some progress on this? I'm not going to claim to have all the answers. What I am going to show you are 3 examples of ways in which we've been working at getting scientific information into disaster risk reduction in a more useful way. And that's involved a lot of working with partner organizations, a lot of back and forth, and a lot of time. And none of these stories have sort of played out to the end yet. These are very much still examples of work in progress. But I just want to touch on a couple of things. We're going to start by looking at landslides after the 2015 Nepal earthquakes. We'll go on to think about what that means in terms of persistent landslide hazard. And we'll finish up by looking at some earthquake scenarios. So we'll start with the Nepal earthquakes. For regional context, I showed you a similar kind of image before. So the solid line here shows you the Himalayan frontal thrust. The yellow patch is the rupture area in the 2015 earthquake. It was a magnitude 7.8. It had a single large aftershock, which was magnitude 7.3, which occurred about 2 weeks later, farther to the east. It did not rupture to the surface, so it was a buried rupture, and the moment was released primarily to the west of the epicenter. And you can see that a little bit more clearly in this image from the US Geological Survey. So the white rectangle here shows a projection of the fault plane, the plane of the Himalayan frontal thrust projected onto the surface. And the colors show a finite fault inversion of what the slip was in the earthquake, or what the slip was likely to be. This blue star is the epicenter of the earthquake on the 25th of April, and you can see that most of the slip occurred to the north and particularly to the east of Kathmandu. And that's important because most of the initial response and most of the initial attention was focused on the epicenter. But the epicenter was at one edge of the rupture plane, one edge of the rupture patch. And actually, the damage near the epicenter was relatively light. Most of the damage, most of the surface impacts were actually felt where the moment was released, primarily in the mountain valleys north and northeast of Kathmandu. So this was the kind of image that was available on the media immediately after the earthquake, a picture of part of Kathmandu city. This is actually Bhaktapur, one of the three cities that make up Kathmandu. Locally, quite high levels of damage, but very local and very spotty. And people very quickly realized that actually Kathmandu was not particularly hard hit by this. It was not the large earthquake that people in Kathmandu and organizations working in Kathmandu were expecting to happen. If you go up into the mountains, though, so into the higher relief part of Nepal, closer to the Chinese border, the damage was locally pretty catastrophic. So this is one example from an area in Sindhupalchok district along the main highway that connects Kathmandu with China, with the China border, and then on to Lhasa. So our interest in this really came into trying to understand what the pattern of damage was, and in particular, what the pattern of landsliding was that had been triggered by the earthquake. Because in the absence of surface rupture, it became clear that one of the main issues in this earthquake was actually due to the landslide. So these light-colored areas that you can see on the slide are all landslides that were triggered during the earthquake on the 25th of April, 2015. So a group of us at Durham, led by Nick Rosser, partnered with the British Geological Survey and tried to map the landslides that we could see as quickly as possible in order to inform the humanitarian response. Really, what we wanted to be able to say was, these areas were particularly hard hit, these valleys were particularly damaged, perhaps even cut off and inaccessible, and these are the areas, therefore, where the humanitarian response should be focused. And that was really helped by the fact that we had already been having conversations with the UN, with the Department for International Development, with these NGOs about what their needs were around earthquakes and earthquake risk reduction. So within a couple of weeks of the first earthquake, we were able to put out a preliminary landslide map. This doesn't show the locations of every single landslide, What it does show is the valleys that were particularly hard hit and the areas that we could see in satellite imagery where clearly there had been a lot of disruption. One of the problems was that even before the monsoon, this part of Nepal has some pretty persistent cloud cover. And so if you're using satellite imagery to map landslides, you need to be able to see the ground. So getting a clear, unobstructed view of the land surface was quite challenging. It took until the end of June to be able to put out a comprehensive map of the whole area that had been affected. And this is the first map that we were able to produce. So the colors on this image show you the density of landsliding that has occurred in each 1 by 1 kilometer pixel. So the hotter the colors, the more landslides occurred within that area. So it's a landslide density map. Again, we're not trying to map individual landslides. That takes far too long. And that's not actually information that's particularly relevant at this scale. The highest values in there are something like 25 to 30 landslides per square kilometer. The yellow stars there show you the epicenters of the 7.8 main shock and the 7.3 aftershock. So these results were used by the UN, in particular by the Humanitarian Country Team, which is the body that coordinates the humanitarian response across the different sectors in which it's active, by the World Food Program in organizing deliveries of food, and by the Nepal Red Cross. And they were particularly useful in targeting these isolated mountain valleys that had been cut off. But there's a problem that we didn't recognize or didn't anticipate before we started. There's quite a complicated timeline here, but I really only want you to pay attention to a couple of things. Time is plotted here on the axis. It goes from left to right. So the main shock on the 25th of April is the left-hand yellow star, and the large aftershock on the 12th of May is the second yellow star. The major UN-mandated needs assessments after a disaster take place within 72 hours and within 2 weeks. So within 72 hours, there should be an initial situation analysis. What has happened? Where are the primary needs? What needs to be done? What resources need to be organized? And that's followed up by a more in-depth look 2 weeks later. So those are shown by these red arrows. We weren't able to produce our first landslide map until well after that initial 72-hour period. And the first complete landslide map, the first complete picture of what we thought the impacts were on the ground, was not until more than a month later. So there's a mismatch here, and an important mismatch, between the timescale over which scientific information is needed and the timescale over which we can generate it with any kind of reasonable effort. And I think that's quite important for us to bear in mind. Okay, so that was the picture immediately after the earthquake. But I've already told you that Nepal suffers from monsoon rainfall and persistent landsliding through the monsoon. So what happens to all these landslides once you start to rain? Remember, the earthquake happened on the 25th of April. It was about 2 months before the onset of the 2015 monsoon. And what we feared would happen has been what has happened. So this is a photograph of an area near the China border. On the left-hand side, you can see the topography as it looked before the 2016 monsoon. There are some small landslides visible, particularly up near the crest of the ridge. On the right-hand side is the same hill slope after the 2016 monsoon, and you can see that the landslides have become larger, and in particular, much of the landslide material has been mobilized and moved downslope in a process that we call debris flow. And these debris flows can have some really catastrophic impacts. So this actually happens to be the house of the local government head in this part of Sindapalchuk district. It's a very well-constructed house. It survived the shaking in the magnitude 7.8 main shock without any damage. It survived the 7.3 aftershock, which was located just a few kilometers away, without any damage. but it's built on a debris flow fan. And so now, during every monsoon, the ground floor of this building fills up with mud and rock. And so it needs to be repeatedly excavated in order to stay useful. It's the right building, it's just in the wrong place. And sometimes those buildings are even more badly damaged than that. So we really need to understand this, because simply focusing on what happens in the earthquake is not enough. And simply focusing on building buildings that can withstand the earthquake is not enough either. So, one of the outstanding questions, scientific questions for us to answer is, when we have a large earthquake, like the Nepal earthquake, what happens to the landslides after the earthquake? How does the pattern of landsliding change? So I showed you before that asymmetric increase and then decrease in the rate of landsliding during a monsoon. Once the earthquake happens, so this red dashed line on the figure, how much more landsliding do we get in the subsequent monsoon? And then how long does it take before we get back to our sort of background condition, what we might expect as normal conditions for Nepal? Or do we ever recover to that background? That's an open question. How also do individual landslides change? We saw the photographic evidence that the landslides had extended, and both headward, but also they'd extended by mobilizing material and having it move down slope into the valley. So how persistent is that, and how long does that process take to work? So we've been working with NSET on a project to map the landslides across the earthquake-affected area during every monsoon, or I should say before and after every monsoon since the earthquake. And I just want to show you a couple of examples what those patterns look like. So this is a fairly small area in Rashua district in the north of Nepal. It's 8 kilometers by 6 kilometers across. It's not chosen for any particular reason other than it's representative of the kind of conditions that we see across this part of the Himalayas. So this is the pattern of landsliding before the earthquake in 2014. You can probably just about make out a few small gray polygons. Those are the levels of landslides that people were used to dealing with. These are the things that happen on a yearly basis. They're relatively small, they occur in pretty consistent places, and there's some adaptation. Communities have adapted to live with them. Immediately after the earthquake, these black polygons show you the landslides that were triggered in the earthquake itself. So you can see, first of all, many of them were much larger, but they also occurred in areas that hadn't previously failed. So there's a much broader distribution across the landscape. After the first monsoon, so after the 2015 monsoon, you can see that some of those landslides didn't change at all, but others, the ones shown in blue here, had begun to enlarge and had begun to elongate. And that pattern continues as we go through the 2016 monsoon and then the 2017 monsoon. So again, some of these landslides haven't changed at all. And in fact, they've begun to revegetate and get covered over and become relatively stable. But others have become a persistent problem for infrastructure and persistent problem for the road network. So this really prompts us to think about how we encapsulate, how we talk about landslide risk, and how we bring it down to a level where it's relevant for people making decisions about perhaps where to rebuild their homes after an event like this. Not every landslide poses a risk. Not every house is downslope of a landslide. And some landslides can impact upon multiple houses. So we really need to start to separate out the ones that matter, the red ones in this slide, from the ones that are perhaps less important. So what I want to show you is an example of how we're trying to do that. So this is a piece of work that takes a database of house locations, houses that were damaged in the earthquake, and that were therefore surveyed immediately after the earthquake, something like 1.1 million separate structures. What we've done is to look at how their proximity to landslides has changed since the earthquake. Are the landslides, active landslides, getting closer? Or is the landslide risk receding? In other words, the active part of the landslide is getting farther away, or is there no change at all? And this is a map that we've generated in conjunction with the local government of a particular local region called the Gaon-Palika, again in the northern central part of Nepal. And this is a zoomed-in view of a part of that. So each dot on this map shows you a particular house. The white dots have no present risk. That's not to say that landslides can't occur there, it's just that they're not at direct risk from inundation by an active landslide. The blue dots show areas where the risk is decreasing with time because we can see how things change across subsequent monsoons. The red dots show areas where the risk is increasing with time as this landslide debris gets closer and closer. So this is something that we're starting to work with the local government to help people to decide where to rebuild their houses. One of the really important lessons of this is that small distances matter a lot in terms of defining risk. Even 10 meters can make a difference between a house which is damaged and a house which is not. So it's knowing which 10 meters you need to move that's really critical. Okay. The last thing I want to talk about, the last example I want to give you an overview of, is at a larger spatial scale. And this is really thinking less about the previous earthquake and more about the next one. What do we do in order to prepare for the next earthquake that will happen in Nepal? Well, if we could predict when and where and how large the next earthquake would occur in Nepal, that would be an easier task, but we can't. So what can we do instead? And this is work that's really led by a researcher at Durham named Tom Robinson, who's looking at earthquake scenarios, but in particular ensembles of earthquake scenarios, and working with the UN, the Office for the Coordination of Humanitarian Affairs, DFID, and a couple of other major humanitarian organizations. Deterministic scenarios are not a new tool. They've been around for a long time. They give us a picture of the losses that would happen if a particular earthquake occurs. So you choose your earthquake, you choose the section of fault that will rupture and the amount that it will slip. You calculate the shaking that results from that rupture. You look then at the potential damage to buildings, and if you wish, then you convert that into an estimate of how many casualties are likely to arise. It gives you a very detailed and reproducible way of assessing where damage is likely to occur and how much damage is likely to occur in that event, in that specific earthquake. What it doesn't tell you is whether that earthquake is the one that you need to be prepared for. So what we've sort of worked with and tried to deal with is the fact that we can't predict where the next earthquake will be. We can't predict how large it will be. And planning for one may not help us in planning for another. So instead, what we've tried to do is to look across the active faults in Nepal, the historical earthquake catalog, and to think, where are the potential earthquakes that could occur? We have, as I said, a decent record of historical earthquakes on the Himalayan frontal thrust. We have a much poorer idea of their recurrence. So how long does it take before earthquakes recur on particular parts of that fault system? And we have much less information on earthquakes that occur in other faults distributed through Nepal, central and northern Nepal in particular. So what we've done is to say, let's assume that all of those earthquakes are possible. Any one of them could be the next earthquake. And in the absence of any information to the contrary, we're going to treat them all equally. And that allows us then to look not at the impacts of one particular earthquake, but at the impacts of that whole ensemble of earthquakes. So we can define different potential earthquake types that rupture different parts of the main Himalayan thrust, and therefore have different total slip areas and magnitudes. We can look at earthquakes that occur off the main Himalayan thrust on other fault systems. In total, there are something like 30 kind of prototypical earthquakes. Sometimes we get at this by moving the same earthquake along and having it occur on different parts of the fault. Sometimes this is switching on a fault in a different part of Nepal. But something like 30 potential earthquakes. Of course, those can occur at different times of day, so we might differentiate between earthquakes that occur on a working day, on a weekend day, and at night, because we know from previous experience that the time of day of occurrence of a large earthquake has a big impact on its impacts, particularly on the death toll. So 30 potential earthquakes, let's say 3 different possible occurrence times, that gives us 90 different scenarios that we can look at. So we take the shaking from those 90 scenarios, we combine that with the numbers and the types of buildings in Nepal, the fragility of those buildings, in other words, the likelihood that they will be damaged, and some estimate of how many people are likely to be inside. That's probably the worst known part of this whole calculation, is where are people? How many people are in a building at a particular time, and therefore vulnerable if it collapses? That's something that we know surprisingly little about. But if we can make some assumptions about that, that gives us an estimate of the potential casualties in each of those scenario earthquakes. And then we can look across the whole scenario and think about the outcomes. So how many of these 90 scenarios cause fatalities in a particular location? How big is the median number of fatalities in that location? How much variability is there between the scenarios? In other words, how much uncertainty do we have about what the impacts of the next earthquake will be? Or do all of the scenarios generate about the same impact? That's the kind of question that we can start to ask. So the lessons that come out of this, I won't go through all the details, but Kathmandu, as the largest metropolitan area in Nepal, is always affected. Someone always suffers in an earthquake, irrespective of where it occurs. In general, the impacts are smaller in the eastern districts of Nepal. That's not to say that there aren't damaging earthquakes that can occur there, but on the whole, across that whole ensemble, the impacts are relatively less. The biggest impacts occur in the central part of Nepal, and particularly in the far west. And that's a real problem, because the far west of Nepal is also the most inaccessible part of the country. The uncertainties are highest in the mountains, and in large part that's because we're not yet including the impacts of landsliding in this. So that's work still to be done. So why I think this is valuable is it shows us the losses which are more or less likely, irrespective of where that next earthquake is. And that can really help us to prioritize the kind of contingency planning that organizations like the UN and others do. So we're working with the Department for International Development to plan hospital retrofitting. Where will medical capacity likely be needed in the next earthquake? That is a useful question to ask, and that guides then the choice of which hospitals should be retrofitted to resist damaging shaking. We're working with the humanitarian country team to plan the emergency response. Where do we need to pre-position supplies? I say we, I'm not doing the pre-positioning, but the organizations that are need to know where they need to put tents, building materials, emergency food, emergency water supplies. And where will the roads be blocked? Where is it most likely that there will be access problems that will prevent World Food Program and others from getting supplies in after the event? So I just want to close with a couple of reflections on this. And I think for me, again, as a physical scientist, the really surprising thing from this work is that the traditional outputs from earthquake science, the kinds of information that we produce, aren't really being used in the ways that we would like them to be used. And I think this really calls for the need for a lot more dialogue between scientists and stakeholders to identify the kinds of outputs that we need to be working on. This is not just our problem, and scientists need to be honest about what we can produce and how rapidly we can produce it, just as policymakers need to be clear about what they need. And they need to be clear about what science can and cannot provide. We can't predict earthquakes, so there's no point in asking. I think the work also shows that there are some really important roles for science at a national level. This advocacy with donors and politicians, awareness, kinds of contingency planning that I've shown you some examples of. All of these are ways in which our information can feed directly into the humanitarian effort and disaster risk reduction. But there is this very real caveat that it's hard to generate information in the aftermath of an event, as we saw from the example of the Nepal earthquake. It's possible, but those links have to be made. And the absolute wrong time to be calling up someone in an NGO or in a UN organization and asking them what they need is after a large earthquake or a large disaster, when they're juggling 50 things and trying to coordinate a response with minimal information. The last thing they need is a scientist coming to them saying, what can I give you? What kind of maps can I make? What can I do? Can I come into the country? Et cetera, et cetera. So we really have to put the effort into making those links before the event actually occurs. And the other thing to say is that this takes time. Earthquake hazard is widespread. Secondary hazards persist for years. We can't expect to get it all right in time for that 2-week initial needs assessment. And trust is really the critical thing here and the kind of undercurrent that runs through these relationships. And there's a real role here for something that hasn't widely been adopted, but I think there is a real need for it. And that is some kind of science advisory group, some sort of trusted network of scientists that groups like the UN or major NGOs can call upon. People that they know will respond and that they know will give them the kind of information that they need. I think Nepal is an unusual example in that the UN in particular is very open to this kind of dialogue. That's not the case everywhere. And I think there's a lot to be learned from this example. So I will close there. I'm very happy to take some questions, but thank you very much for your attention.
Well, thank you, Alex. We have a few minutes. We could take a few questions if there are any here. It's a big auditorium and it's a little bit intimidating to ask a question here, so maybe I'll start and see if anyone follows here. With your first point about making contacts with stakeholders and learning, providing information for them, I'm just curious with a country like Nepal, is it what's the most useful organization to talk to, the high-level government or the local communities in terms of knowing what they need? Who's making the decisions?
Yeah,
essentially.
So the question is, who's making the decisions about scientific information? The answer is both. That's not a very satisfying answer. But different decisions are being made at different levels. You cannot work in a country without agreement with the government. And Nepal, for all the weaknesses of the central government, is no different. And so government engagement is absolutely necessary at all stages of this. Engagement with the UN as the kind of agreed coordinating body, the organization that probably has the best kind of overview of what's actually happening across the country, that's critical as well. But at the same time, those decisions are going on at a remove from the kinds of communities that are actually exposed to these hazards. And so there's a real role here for sustained engagement at the community level as well. I think one of the things that set this project apart, and one of the things that partners in Nepal remarked upon repeatedly, was they said, you guys keep coming back. It was a 6-year project, and they're used to people coming in for 18 months, 2 years, maybe 3 years at a stretch, extracting some information, writing up some papers, and disappearing. We kept showing up. And actually just showing up and being, in the door makes a huge difference. So I'm not pretending that it's easy, but I think, you need to think about what are the decisions that are being made, and then that sets the appropriate level at which you engage.
Good. Any other questions? Matthias?
You mentioned that road construction is actually a source to landsliding.
Yes.
Is this purely an engineering problem that could, because of the limited capabilities, and that could be improved by better road engineering? Or is this something that science should get involved in actually planning where to put the roads in the first place?
I think both. So much of the rural road construction is done without much geological input, it's safe to say. And decisions are made sometimes politically, sometimes as a matter of expediency about where to cut a road. Having said that, the types of remediation that are often applied are not particularly relevant. So there are some organizations that are working, for example, to use bioremediation to stabilize hill slopes, or gabion boxes and this type of thing in order to prevent landsliding along some of the road corridors. That's fine for some landslide hazards, but it's not particularly useful, for example, for a deep-seated bedrock failure. So I think there's a role for science in the planning stage, in the kind of the initial design and layout of the road network, but there's also a role in terms of what can actually be done to stabilize some of these hill slopes. And I don't think we've engaged particularly well at either side of that problem. Yeah.
Good. Yeah.
Maybe last time. These hazard maps are really interesting. In Europe, we have many countries which are also earthquake prone. So how widespread are these maps? We do have it in the States, but what about Turkey, for example?
I have to be careful what I say. Hazard maps are very useful, but I think we always have to think about how they're being used. So probabilistic seismic hazard analysis, for example, has come in for a lot of criticism recently. But it was designed to do a very particular thing, which is to set an expected level of shaking at a particular probability over a particular time period. And with sufficient data, with sufficient knowledge of the faults and sufficient earthquake record, that can be done to a reasonable degree of precision. One of the problems in Nepal is that when PSHA, when probabilistic seismic hazard analysis, has been done in the past, the results depend a lot on the input data. So you end up with hazard maps that look very different, caused by slight differences in whether a particular earthquake catalog was included or not. Now that's a scientific issue, and we can argue about the best way to do this. The problem then comes when you put those maps before a policymaker, and the policymaker says, well, these maps are different, so which one do I believe? And the default response is, well, neither of them. Neither of them are telling me what I really need to know. So I don't want to give the impression that hazard maps are useless, and they are clearly used in many different settings. But for the kind of high-level operational decisions in a place that's prone to hazard like Nepal, I think we need to look more carefully at this and think about what kind of outputs, in addition to those, we need to be generating as scientists.
Okay, yeah, one last one.
You talked a lot about humanitarian organizations, transitions, and scientists, but I would like to know how you can engage with the people who actually live there and are at the highest risk of being in danger. Is there maybe a problem with the cultural engagement as well, as like with the politicians and
So a lot of the work that underpinned what I've shown you here stemmed from a couple of projects looking at risk perception and community-based risk reduction efforts in Nepal, going back a decade or more. So this is work that my colleague Katie Oven was heavily involved in. And that takes time. So, going into communities, asking what their priorities are. What are the risks that they face on a daily basis? What's their awareness of the hazards that are posed by earthquakes and landslides? And how do they rank those in relation to the kind of everyday risks? And I think one of the really important findings that comes out of that is that, people will take steps to make themselves more resilient. But they're not going to take steps to make themselves more resilient to a rare high-magnitude earthquake if it puts them at greater risk from a shorter term or more immediate threat. And it seems obvious when you say it. People will focus on what's in front of them. But it's something that I think we forget a lot as a community. So we come in and we say, you need to worry about earthquakes, or you need to worry about landslides, or you need to worry about floods. depending on what we've been funded to study. But of course, this is happening within a much more complex landscape of risk. So I think taking the time to find out what that perception is, what that landscape of risk looks like, and then thinking through ways of engaging so that you're not making people less resilient is really important. So one of the things we've been doing, for example, is working with communities to make measurements of landslides that are close to the community so that they can begin to understand something about when those landslides move, what kinds of events trigger that movement, and what they can therefore do. But again, you have to understand how that landslide is viewed and how important it is and what all the other concerns are before you can do that. That's a really good question, though.
Good. Well, there is a reception waiting for us, and I think we should thank Alex one more time for taking the time to come.